We have many things to do. Good afternoon, everyone. A few things to say this last day of class, and it's about the final exam. It's going to be in the pharmacy building, and this is the room. You can go also check again this into the final exam website with a unique code. So you will see where the room is going to be, and again it's going to start at 2 o'clock sharp, okay? So please be on time, and remember, wait outside, we'll call you in. A few more things over here. We are just at the end of the contents, and there is no lab this week, and we're going to talk today about reservoir depletion and injection. So this is the last topic. I already uploaded that on the website, but I have some problem with the images, which I already figure what's going on. It looks like my code doesn't like the JPG figures, so that's why they are not in here. But I have also already uploaded the PDF version of this, and I will fix the HTML version hopefully today. So if you go to the PDF version, you will be able to see the JPG figures. So we're going to the last chapter. Right, there you go. So there you have the figures about which we're going to talk about today. Let me see, what else? Also about the exam, I told you that I would not give you a practice exam because it's the final exam. And here I uploaded a study guide, okay, with typical questions for the theoretical part, and also which kind of problems you could expect. It's not going to be anything out of this, all right? And it's everything, it has been done already, either in the problems in the notes or in the homework. Again, field tests, just mechanics about hydraulic fracturing design, and reservoir depletion, which is the last topic that we're going to talk about today, which it is not very long, so we'll be on time to cover that one. So you have everything in there, you just have to prepare for it. And those students that are not doing very well and maybe below the D letter grade, please come and talk to me, okay? There is still time to fix this. There is just one or two, but make sure that you don't want to fail this class, especially if this is your last semester. Good news about grading. As you see in the syllabus, there is here a 10% which goes for quizzes and attendance. I'm going to give you all that 10%, okay? So you can count with it. When you, you're lucky because still I'm working on implementing something to take attendance through an app or through like a Twitter, what's the name of this? To a Twitter poll or something like that. But I didn't get to do this yet. But you're gonna get a 10%, all right? So when you compute the grade, I'm gonna use exactly this formula, okay? 15% homework, 10%. You're gonna already get that. 15% lab reports, 20% exams for each of them. Talking about grades, so we have the final exam on Wednesday, and I'm going to grade exams that same afternoon. After you finish, I'll stay with the TAs and grade it, so you'll have that right away. Probably towards the end of the week, on either Thursday or Friday, I will also upload your letter grade as soon as possible. So if you want to take a look at your final exam, if you see there is a problem with the grade or that's not what you expected, please come to my office and you'll be able to see your exam. Okay? All right. So if there are no questions about exams and grading, I'll continue with the lecture. No? All right, okay, good. So I just want to talk a little bit about microseismicity, especially because on Friday I forgot to record the lecture. So for those that didn't see that part, I just want to remind you very quickly that we talk about what is the origin of microseismicity, which is basically shear failure. In many formations, especially in unconventionals, we see that there are pre-existing fractures or planes of weakness that whenever the fracture gets close and deforms a rock around the fracture, or some of the pore pressure within the fracture gets into those pre-existing fractures, they reactivate in shear. And that releases energy through elastic waves that we measure as seismicity, which most times is very small. And something that we said is that we can use the size of that microseismic cloud that we call SRV in order to tell what is the estimated ultimate recovery, which most times or in general is not going to be in a straight correlation because there are some outliers, but many times, especially if you know your formation, you could establish a trend of what is the estimated ultimate recovery with the stimulated reservoir volume. And if you do that, you can calculate EUR based on the typical equation that you use for conventional formations, but now you have to take into account that the volume is going to be the SRV. And it's not directly the volume of the net pay. That could give you, in general, your recoverable oil in place, but what you're going to actually recover depends on how much you stimulate. If you don't do any stimulation, just put a vertical well, you're not going to get this amount of oil. You need to stimulate that formation. All right, so with that, we end hydraulic fracturing. And now we're going to start talking about reservoir depletion. And probably reservoir depletion is a topic which is, it makes most honor to the name of the class, which is Reservoir Geomechanics, because it's basically a way to use geomechanics into understanding better reservoir engineering. Okay, so for reservoir depletion, what we want to do, our objective is to predict what is going to be permeability as a function of time, when time means that you have depletion. We have a variation of pore pressure. And we know that we can link permeability sometimes to porosity. So if we can find and calculate porosity, we can tell what is going to be K. And since we are varying pore pressure, we know that this porosity and permeability is going to be linked to effective stresses. So if we can calculate those effective stresses, we're going to be able to tell what is the variation of porosity, what is the variation of permeability, and very important, what is going to be the impact of that variation on decline curves. So that's our objective, to take into account geomechanics in order to predict production rates and to see how geomechanics can impact on that. All right, so let's get started. I'm going to make a schematic here of a formation, And let's imagine that we are somewhere offshore. Sometimes these problems of subsidence are important in offshore locations because sometimes you have shallow formations and they are relatively soft, and that makes this problem a little bit more serious. So let's say that we have here a sand that's going to be subjected to depletion. Basically, we want to produce out of that sand, and we do that by doing what? How do you manage to get the fluids to go up the production casing? If this is time, what are you going to lower? The pressure, right? So your pore pressure, if this is your initial pressure, once you start production, is going to go down with time. And because now you have a lower pressure here, this is going to induce the fluids to move into the wellbore, but the pressure now is going to be lower here than there. Okay, if you lower the pressure in this formation, what do you think is going to happen with stresses? Let's say that on top of this sand there is a shell with a very low permeability. So we lower the pressure here. What do you think is going to happen with the effective stresses inside here? Probably I made this too high, but yes, I heard some people say something.
It should increase.
What is going to increase? The effective stress. Notice that the total stress is just the overburden, and even if we change the pressure here, whatever we have on top is not going to change. All the water is going to still be there, all the sediments are going to still be there, but it's just that if we lower the pressure, now effective stress is going to increase inside the reservoir. And if effective stress is increased, what's going to happen with this rock? It's going to deform, right? It's going to compact. So remember, always strains are proportional to stresses. And this is going to result in the formation. Let's imagine that all the formation was depressurized to a constant value, so everything is going to go down. The new volume of the reservoir now is going to be this one. And what do you think is going to happen with the sediments that were on top of this one? If this one goes down, the shell has to go down too, right? And so you cannot make a void now. So if everything goes down, sometimes if you're near a fault, you will see that depletion sometimes also causes fault reactivation. There is some data. There is a very good example of the problems of depletion in California, in Long Beach, where they were correlating induced seismicity to production, and it was a very good correlation. Basically, every time they were depleting, the formation was compacting, and that was dragging all the sediments which were reactivating nearby faults. If all of this goes down too, what we see also with severe cases of depletion is that the surface, the top surface, the ground surface, or the seafloor surface can also go down. And this is called subsidence. For example, in the North Sea, sometimes they have to jack up some of these offshore rigs if they have the foundations on the seafloor. In some places, it's not too deep, so they are directly anchored in the seafloor, and they have to jack them up in order to keep them at the same height because the seafloor goes down. And in this case, I was telling you, in California, in Long Beach, it was a ground surface that actually went down by, if I remember correctly, more than 20 feet, which is a lot, okay? So our objective is going to be to predict how much this top surface is going to go down, how much stress are going to go up, and we'll not talk much about subsidence because that's a different, not a different problem, but it requires some other things. Something else I like that you keep in mind for production is that sometimes when you have a lot of compaction, this can also cause your production casing to buckle. You know what is buckling, right? Mechanical instability, like columns, when they have a lot of compression, they buckle because they get flexion and they fail like that. And imagine that also you have from this offshore rig, and if there are some seafloor facilities somewhere over here, if you have another wellbore going in this direction, if you have compaction and this fault reactivates, here you could get wait, I did it the wrong way, but let me fix it. You could get casing shearing. Basically, at the beginning you had the casing going through the fault, but when it reactivates, it can cut it like butter. It's not going to be any problem for the rocks to cut that casing, and you will lose that wellbore. So it's not going to be, it's going to be bad. Most times you need to control that. All right, so let's see how we solve this problem. First, let's try to understand this in terms of strains. And let's assume we're going to simplify our problem to just a one-dimensional case. What is delta H divided by H in mechanical terms? Strain, very well, and now we're going to add a coordinate system 1, 2, 3. So which strain is delta H divided by H? Epsilon 3, 3, right? With the assumption that all the surfaces, all the top surface goes down the same amount, and there is no displacement on the horizontal direction 1, 2, what is going to be epsilon 1, 1 and epsilon 2, 2? 0. And if you remember, this is what we have been calling also for a long time the one-dimensional strain condition. And we already saw some equations that help us to solve that. Actually, this is the one that we use to calculate stresses as a function of a tectonic strain. Okay, so we're going to have to do something a little bit different this time, okay? But before I go to that, let me emphasize what is going to happen when we have depletion. Before we actually show that with the solutions, if we lower the pore pressure, we will have compaction. And compaction is going to be basically the porosity decreases, and it's a result of effective stresses increasing. Sorry. If porosity decreases, because we have a process of compaction, we're going to have a decrease of permeability. We know that. And you may remember this from just, you remember the Kosenik-Karman equation? Kosenik-Karman equation tells you that permeability is proportional to porosity and also to what? What is the most important parameter in the Kosenik-Karman equation? What? Grain size, okay, but there is, the pore throw size, right? And that one is square. So if we decrease the porosity, we know that the pore size is going to get smaller, porosity is going to get smaller, and permeability is going to get smaller too. Sometimes we can use these equations, but some other times we can take a shortcut, and instead of using porosity, we can use directly stresses. And this is going to be especially advantageous for the case of fractured rocks. In fractured rocks, permeability is proportional to what? Do you remember what was the equivalent of Kosenik-Karman for fractured rocks? If you have a fracture, you're going to have a fracture. Yes, but that depends on what? In the width of the fracture. And do you remember the exponent of that? No, it's cube. So for fractured rocks, increasing stresses and reducing the fracture width, it's a lot more important than for granular media. That's going to decrease your permeability a lot more than in granular media. But sometimes measuring fracture width is kind of difficult. So we're going to use something different, which is a law that directly tells you what is permeability as a function of effective stress. And usually you can write equations in which the logarithm of permeability is related to effective stress. The bigger the stress, the lower the permeability. And because it's in logarithmic scales, that means that it decreases a lot when you increase stresses. And this is the type of law that we're going to use in the homework, okay? I'll give you later, I'll show you the exact equation for this. Again, how is this going to affect us now from the point of view of production is that if you were to, for example, you do all the formation evaluation analysis that you need. You have porosity, you have everything. You have permeabilities, relative permeabilities, and then you say that the decline curve is going to be something like that. Well, if you have some of these formations where they are very sensitive to stress, stress may lower the permeability quite a bit as you start depleting. So this may be with no stress sensitivity, but probably the actual one that takes into account stress sensitivity is going to be much less than that, because this one takes into account that sensitivity takes into account that permeability is a function of the pore pressure. Sometimes you can input this in CMG through what is called permeability tables, and you tell the simulator what is going to be permeability as a function of the pore pressure in order to predict correctly what the decline curves are going to be. Okay, this is as far as we're going to go in this part of the theory, but for you, for practical knowledge, remember that for unconventional, this is very important, because the permeability in unconventional depends a lot on fractures, either propped or unpropped. And you can do these same curves for unpropped fractures and also for propped fractures. So let's just add one more curve over here. Probably, if this one is with proppant, is going to be much higher than the one without proppant, but it can reduce a lot too due to stress. What happens to prop fractures when you increase a lot the effective stress? Mr. Nolasco, you have the answer?
Oh, no, I had a question.
What's your question?
Explain.
Yeah, what I mean with the stress sensitivity is that permeability is a function of pore pressure, or which is the same, the permeability is a function of the effective stress. So if effective stress go up, the permeability is going to go down because your medium is tighter.
When would a rock not be stressed?
For example, if you have a very tight sandstone where the porosity is very small and your pores are already quite small and not very much influenced by stresses, because all the stresses may go onto the solid rather than reducing the pore size. So there are some rocks that for the same change of stress, the change of permeability may be very small, that there are some others in which it might be quite big. Okay, so why would the permeability of a prop fracture get reduced with increasing effective stress? Can anyone give me an example? What happens to proppant if you increase a lot of the stress?
The pore changes shape, maybe?
Changes shape, and that's usually known as proppant crashing. If you increase a lot of effective stress, the proppant is just going to crash. Actually, there are some of these synthetic proppants that are manufactured that have a higher strength, so they do not crash when you start depleting and effective stress go up. And what else? If the proppant is very strong and the rock is not, what's going to happen with the proppant?
It'll deform the rock itself.
Yes, and that's called proppant embedment. So these two, either a proppant crashing or proppant embedment, are no good. And if you do not design well a completion job, your decline curves may be quite steep, much steeper than what they would be with the proper design. Okay, so let's see how we solve this problem. And you remember, I hope, this equation very well. Effective stress is equal to total stress minus what? Pore pressure. And this is a tensor notation, and I mean all the stresses, the 6 equations, normal and shear. This is what is called Terzaghis effective stress. In the 50s, there was a gentleman working for Shell that realized that this equation was not very accurate and found that there is a coefficient that corrects that, and it's a coefficient alpha, which is between more or less 1 and 0.5, which is called the Biot's coefficient. And because he came up with this new equation, this is called Biot's effective stress. It's a more accurate definition of effective stress, and this is what we're going to have to use in our equations. So what is the Biot coefficient? The Biot coefficient tells you more or less how much of the strain goes into the pore and how much of the strain goes into the solid matrix. If most of the strain goes into the pore, that means that the solid is much stiffer than the pores. And that usually happens with soft rocks. So for example, in unconsolidated sand, quite before deforming the grains itself, you're going to deform the porosity. And in that case, the Biot coefficient tends to 1, and these two equations are more or less the same. However, when you start to have very small pores with a lot more solid than porosity, this coefficient starts to get lower and lower, which means that deformation goes onto the solid matrix and also on the pore. And this usually is valid for very stiff rocks. So for example, very stiff shales, particularly if you look at small piece of rocks, they will have a very low Biot coefficient. Okay, so what do we do with this now? What we have to do is we have to solve the equations of stresses as a function of strains. So basically, we're going to use linear elasticity to solve this equation. Stress equal to stiffness times strain. And we're going to use our new definition of stress, effective stress, and this is going to be S11 minus alpha pp, normal stress in direction 1, normal effective stress. I'm going to have the same for the other direction. Remember that here 3 is the vertical direction. We'll also have our shear stresses, which are not affected by pore pressure, and the stiffness matrix is the one that we have used before, assuming linear elasticity and isotropic media. And if you remember, it looks something like this. Where this is 0, this is 0, and I don't care about this one because we're not going to use it, okay? What I do care about are the strains. Here we have epsilon 11, epsilon 22, epsilon 33, epsilon 12, epsilon 13, epsilon 23. What was epsilon 11 and 1 and 22? 0, and epsilon 33 was not 0, right? So this is the 1D strain condition. So since these two are 0, we're going to be able to solve these equations. What you're going to see is that the third row basically tells you this. Strain is equal to this thing divided all of that, right? So strain, and that's what we were looking for, is effective stress divided this stiffness value. And do you guys remember what this is, all of this?
E prime.
No. I'm glad that you remember E prime. That's called the plane strain modulus, but it's not the one that we. No, this was M, if you remember. M, constraint modulus. Okay, I'm interested in the following. What did we say about S33? S33 is the overburden. It's a weight on rock on top of the reservoir. It is constant, right? So what I'm going to do is I want to calculate what is the variation of strain with the variation of pore pressure, because that's what I'm going to change. And what is going to be that? It's basically the derivative of all of this with respect to that. And I know this one is constant. So it's just going to be alpha divided by m. So if I want to calculate a change of strain given a change of pore pressure, I just multiply this times the change of pore pressure, and I get the answer. And if I combine the first row and the third row, those two equations, I'm going to get to something that we already know quite well. That is that the horizontal effective stress is going to depend on the Poisson ratio through this coefficient that we already know. But I'm going to use the definition of effective stress as over here. And I'm going to use also total stress for this one, so that one. And I'm going to find that the horizontal total stress is going to be equal to this notice that this one just went to the right hand side. On this side is effective stress, and this is all the same. So I'm going to do the same thing that I did before. My question is, what is going to be the change in horizontal stress due to change in pore pressure? Because that's what is going to change. Again, S33 is not going to change, and all the rest are just constant variables. So when you do the math over here, you will see that we just have this Poisson ratio divided 1 minus Poisson ratio times this negative alpha plus a positive alpha, and this is going to lead to this equation. And with this equation now, with these two equations, we can tell what is going to be the strain due to a change in pore pressure, and also what is going to be the variation of total stress due to a change in pore pressure, where that coefficient is going to be depend on both on the Poisson ratio and on the coefficient alpha. So let's stop just 1 second and try to understand this coefficient. What does it mean a Poisson ratio equal to 0, for example? Yeah. Correct, right? So notice if this is equal to 0, then this is going to be 0, 0, and this is going to be 1. It's just going to be the variation of, it's going to be equal to the Biot coefficient. And that will mean that the change in total stress is just equal to the change in pore pressure. However, this one is going to be in a smaller number whenever the Poisson ratio is different than 0. And that means that when you start to deplete, you compact the rock in vertical direction, but that compaction in vertical direction makes the rock expands also in horizontal direction. And that's going to make this response different. So, with these same equations, also we can tell what is going to be the variation of effective stresses. And I think it's much better to understand first effective stresses and then the total stresses. Oh, yes. The variation of the horizontal stress with pore pressure is just going to be negative alpha Poisson ratio 1 minus Poisson ratio. And this is just math, okay? Here you have to replace the previous equation that we used before. And the variation of vertical stress with variation of pore pressure is just negative alpha, which is, this is just the definition of sigma 33, which is S33 minus alpha pore pressure. What these equations mean is that whenever you have depletion, say that this is your horizontal stress, this is your vertical stress. At the beginning, when you have depletion, delta P is going to be negative or positive? Negative, right? Because the final pressure is going to be smaller than the original pressure. This is going to be a negative value. Negative times negative is going to give you positive. So the increment in those effective stresses is going to be positive. And for a typical Poisson ratio, if you remember, if we say this is 0.25, this is going to be 1/3. So that means that what's that? Don't worry. So if we change the pore pressure a given amount, let's say the alpha is close to 1, let's say 0.9. I change the pore pressure this amount. The effective vertical stress is going to increase almost all of that, but the horizontal stress is just going to increase 1/3 of that. So the new Moore circle now is going to be like this. And this one is going to be sigma HF, and this is going to be sigma BF, where with sigma H I refer to sigma 1,1, and sigma B I refer to sigma 3,3. So as you deplete, the Moore circle is always going to grow towards the right, which means more compression, and it's also going to move up, which means more deviatoric stress. And if you remember that we said that whenever we have a lot of compression, sometimes we can run into this compression limit, that if your Moore circle goes beyond that, you start to have grain crushing. So we're not going to get into that, but remember that that was something real. And this one is the shear one. Some people suggest that sometimes also you can go into this direction and get into shear. That's a little bit too under debate, but some people argue that you can also go into shear by depletion. So, very important, remember, depletion is always going to increase effective stresses, both horizontal and vertical, but the horizontal stresses are going to increase less than the vertical stresses. And that's going to make your Moore circle to get bigger, because the difference now into horizontal vertical effective stress is going to be larger. Okay, yes?
Does changing the stress regime change that?
It would, because in that case, probably you may start with your vertical stress here, like the smaller one, and your horizontal here. So it will change the variations. Yes, you're right. This is valid. Thank you for that, for normal faulting and strike slip. All right. This is very nice conceptually. It makes a lot of sense. But however, this is not what you can measure in the field. If you really want to see what is the variation of stress in the field, what you have to do is you have to measure the horizontal stress. And if we are in these two cases, the horizontal stress is going to be horizontal, the minimum total stress is going to be horizontal. And how can you measure that? How can you measure the minimum, or in general, the least principal stress? How do you measure S3? You have to know that, guys. With the frag test, right? So what you really measure in the field in order to capture these effects is total stress. So there is an alternative stress path plot for this. And this is what is called an effective stress path. That means how the stresses change as a function of time with depletion. But you can also make the following plot. Here you have pore pressure. Here you have total stresses. You start with a given value of the vertical stress and a given value of a horizontal stress. And as you deplete, you're going to move to the left, right? What's going to happen with the vertical stress, total vertical stress? Nothing. It's going to be constant. And what's going to happen with the horizontal stress? Will it increase, decrease, stay the same? Here is the answer. These are all positive, this is positive, and if this is negative, this one is going to be negative. And what this equation tells you is that the horizontal stress is going to go down with a rate equal to A, where all this thing is A. So the total horizontal stress is going to decrease. And this is very important because if you remember when we were talking about pore pressure, we said that whenever you have depletion, your fracture gradient goes down, and that's because your horizontal stress goes down. If you drill through depleted regions, your local stress is going to be lower than you would expect without depletion. And that sometimes can make the drilling window to be quite narrow. So let me see, I have an example here, just to finish this part with actual measurements. So this is what I was showing in my drawing, and here's real data where you see how horizontal stress, total horizontal stress, decreases with pore pressure. For this is a case in the North Sea, and all these points are measurements done with hydraulic fracturing. So, guys, here you have an example of what a problem of that would be. So it's very clear here in the solution. If you have any questions, again, just send me an email or stop by my office, and I will answer that. But this is just an application of what we did conceptually. Okay? You have one question?
I just asked, do you still have outside order next Monday?
Next week?
Yeah.
Yeah, I'm gonna be there. I'm gonna be there. All right, guys. Thank you, everyone, for all your time. I'll see you if you're going to senior banquet on Friday, and if not, I'll see you on Wednesday. And just send me an email if you have any questions. Okay? Or stop by my office. See you guys.